Welcome to IS 300. This week we're talking about architecture for an enterprise Internet of Things. Our keywords for this week are IoT architecture, monolithic architecture, microservices, and IoT middleware. As you recall, in previous chapters we talked about IoT applications for consumers, primarily healthcare and home automation. We also talked about industrial IoT, which is ideal and well suited for manufacturing, supply chain management, industrial engineering, and oil or gas utilities. This week we have defined in the textbook a reference model which breaks the enterprise IoT into layers. 5 layers to be exact that are listed here. The user interface and external communication layer, the application management layer, the enterprise service bus or the middleware layer, communication and networking layer, and the device layer. We'll break these layers down and we'll start at the bottom of the stack with the device layer. The reference architecture recommends that each device must have a way to identify it, a universally unique identifier for every device. That can be on the chip of the device itself, hardware. It can be on the firmware, or in this case, the EEPROM or the EEPROM, electrically erasable, programmable, read-only memory. Or it can be a MAC address if we're talking about Wi-Fi, smartphones, tablets, PCs, and devices of that nature. Every one of them, if they're communicating using TCP/IP, there is a MAC address and an IP address, which makes them uniquely identifiable. The communication layer is going to be some familiar protocols that we're familiar with, such as HTTP or the Hypertext Transfer Protocol, which sends and receives or posts and gets from devices using typically a 32-bit transmission. There's also something referred to as MQTT, which stands for Message Queuing Telemetry Transport. It is ideal for sending messages across smaller devices, weaker networks where data loss and connection loss might be infrequent, using some wireless technologies and or Bluetooth. Or there's something called the Constrained Application Protocol, which is also designed to use HTTP for sending information over the web using low overhead and simple messaging. The enterprise service bus or the middleware layer is the bridge that allows communication from different devices and sends it to the appropriate destination. It supports both HTTP and MQTT. Both of those protocols are represented in this layer, and it also provides support for legacy protocols. It is the gateway to communicate between the other layers using middleware or APIs. The user interface, usually graphical user interface, not always, but if you're talking about a web-enabled device, there will be a graphical user interface or a GUI. Then technologies like Ruby, Python, Java are used to build applications. There's also an API management system on this layer, which handles application programming interfaces and or middleware. So there's communication between the other devices and the user interface using some sort of external communication functionality. Middleware is the key to allowing IoT devices to provide data analytics and information that can be used for purposes of business intelligence and analysis of the inputs and outputs of these devices. It makes communication possible among disparate elements that would normally not communicate with each other. It encodes and exchanges information between the devices and the sensors. It acts as a communication platform that allows the sensors to send and receive data that's needed for purposes of data analytics. It is critical for end-to-end communication. Here's a diagram which is, I think, very useful in describing our reference architecture. At the bottom of the stack are the devices and the protocols, networking and communication. There's HTTP, there's UDP and TCP, MQTT, which we talked about earlier, the message queuing, telemetry transport, transmission control protocol, which is TCP, user datagram protocol, which is UDP, connectionless protocol. TCP is connection-oriented, UDP, connectionless, typically used for SMS and queuing of messages and things like that. The XMPP stands for Extensible Messaging and Presence Protocol. It is a set of, again, instant messaging and chat, voice, and video calls that would typically be used on some sort of a device, such as a smartphone. Then there's Constrained Application Protocol, or COAP, at the bottom of the stack, which is also designed to communicate over HTTP for simple integration with the web. Most of the devices at the bottom of this stack are going to be able to communicate using some sort of a web-enabled protocol. As you go up the stack, there you have the enterprise service bus, or the middleware layer, as we talked about earlier. Service-oriented architecture, which is SOA, is basically used to allow services to be provided that can be called upon, and not so that for purposes of not having to reinvent the wheel, you use the service-oriented architecture and you rely upon services that already exist. Services such as the shopping cart, which we're familiar with, is a service that would be used and called through a service-oriented architecture. The monolithic versus microservices we'll talk about in just a minute. As we go up the stack, we get to the application itself. The application will include the business logic and the database and or cloud computing components that are required. And then at the top of the stack is the mobile interfaces, the web interface, wearable devices, and or external applications. Again, all of these will be web-enabled user interfaces, graphical user interfaces, or GUIs. Monolithic software has been around for quite some time. Windows users might be familiar with COM or DCOM, distributed COM. And that was one of the original middlewares, which was intended for purposes of communication, standardization, model independence, but monolithic architectures acted as a united application, a single application, which meant that if you needed to improve performance, you had to have multiple deployments of the same application, which created overload and bottlenecks, and so it was not very efficient. And if you had to redeploy complexities as a result of multiple deployments of monolithic architectures was problematic in terms of maintenance and integration. First, let's talk that first. The user interface at the top sends data to the business logic layer, which then communicates with the data access layer, which communicates with the database, sends and or receives data from the database, sends it back up the stack to the data access layer, which processes it through the business logic layer, and finally displays the information through the user interface. This is common send and receive of data that we use all the time, whether we're using mobile devices, smartphones, tablet PCs, or any other type of device. This is what happens. With microservices, now you have decoupled processes that communicate through what's called language agnostic, which means doesn't matter what language, it is language independent and platform independent through the use of APIs or application programming interfaces. It is a way of breaking applications into manageable bite size, if you will, executables instead of in-memory function calls. There are separate processes that use lightweight mechanisms, typically XML type applications such as the REST API. We looked at a REST API in the previous chapters. Before the exam, there was a tutorial, I believe, in week 4. Several companies, successful companies, have migrated to microservices, including Netflix, eBay, Amazon, Twitter, PayPal. These are all companies that we're all familiar with, all very successful, and all have integrated and implemented microservice applications to improve maintainability and continuous development improvements and integration. Here's an example of a diagram that implements or displays an implementation of microservices. You have a database at the bottom, just as you do with monolithic applications. You have the database which goes to the microservice. The microservice, one or more microservices, then will handle the processes of sending and receiving data across from the database layer to the service discovery and management layer to the interface layer. And so this layered approach of breaking applications into smaller, separate processes is very efficient. Traditional architectures cannot meet the requirements of heterogeneous, interoperable, customizable, and scalable systems, and so microservices has been developed for purposes of decomposing IoT systems into smaller tasks. Cloud-based microservices create an IoT model which is much less complex, and so you have sensors and actuators who communicate with devices, and those devices can send and receive data from the sensors and the actuators across a network for purposes of analytics, data analysis, and or simple communication by disparate protocols. You can also even integrate third-party systems such as customer relationship management systems and ERP systems. It makes for an extremely functional and effective way for IoT, enterprise IoT devices to communicate. Microservices, here are the characteristics. Autonomous, they're independent of each other and they can function without affecting each other. So if one device or one process goes down, systems can still function. They are specialized. Every device has its own set of capabilities. Agile, so that they're small and independent, flexible, easy to deploy. It's no longer necessary to use a simple technology or the same technologies or the same platforms. They are resilient and independent. This is a nice chart that compares monolithic architectures to microservices. The monolithic is simple to test and deploy, but gets complicated as the system becomes larger. Microservices are a little more complicated, but they're not intended for simple applications. Monolithic applications, on the other hand, are limited in size and complexity. Microservices are scalable and they can grow as needed, and they adopt well even as the application becomes more complicated. With monolithic services, you have to redeploy the entire application after each update. With microservices, you only have to deploy the new upgraded process, but not the entire application. With monolithic services, continuous deployment is difficult. With microservices, it's designed for continuous deployment. Monolithic is not as reliable as microservices. Microservices, you can isolate a problem and fix it without affecting the other entities. New technologies are difficult to adopt with monolithic services, but easy to adopt with microservices. Database operations are simple. With microservices, you can use more complex business transactions that are updated frequently and can be owned by different services, and they are distributed. In a nutshell, microservices is the way to improve upon the enterprise Internet of Things and is the wave of the future, while monolithic applications are basically the past. In summary, the migration from monolithic to microservices is not necessarily a simple process, but it is a process that will pay off over the long term. The return on investment with migrating to microservices is significant. Many companies, again, we talked about eBay, Amazon, Netflix, and companies of that nature, have been very successful with using microservices. And middleware layer concerns can make the enterprise IoT more efficient, because the middleware can allow communication to exist between different layers of the new architectures. This has been the discussion of Chapter 5, Architectures for Enterprise IoT.